My name is Keegan Furlong, and I'm delighted to be here today to discuss the crucial role of bioengineering, energy, and carbon capture and storage, or BECCS as it is known, in shaping effective environmental policy. Today, we'll delve into how my research can inform decisions to achieve a net zero target with negative emission technologies, or NETs, NETs. Next slide, please. So, before diving into the specifics of BECCS, let's briefly review the public policy cycle. This cyclical process provides a framework for addressing societal issues through government action. It begins with problem identification, followed by policy formulation, adoption, implementation, and finally, policy evaluation. Effective environmental policy relies on robust evidence at each stage, something NETs like BECCS can deliver. Next slide, please. BECCS represents NET that could help the UK achieve their net zero goal. It does this by combining biomass energy production with CO2 capture and storage, effectively removing carbon dioxide from the atmosphere while generating power and growing your fuel source. The BECCS value chain encompasses biomass production, transportation, bioenergy conversion with capture, and CO2 transport and storage. My research focused on optimizing various stages in this chain. Next slide, please. So my MSc dissertation focused on a comprehensive life cycle assessment, an LCA, and a cost analysis of BECCS. The study had three primary goals: to evaluate the environmental impacts, assess the economic viability, and identify key hotspots in the BECCS lifestyle. Next slide, please. Climate change has a causal chain and a response chain. So the causal of an impact of the climate change, trapping heat from fossil fuels burning. So the obvious process is fossil fuels burn, the CO2 is released, that creates a barrier where light from the sun is able to enter, but has issue reflecting back into the atmosphere and back out in space, and causes the temperature to rise. This is known as the greenhouse effect, which is why they are called greenhouse gases. So the response to this has been more environmentally friendly energy sources, practices on trying to capture CO2, reduce solar radiation management, and prevent and minimize issues. Next slide, please. So this is the climate change pressing global challenge. The Glasgow Climate Pact emphasizes the need for accelerated action to limit warming to 1.5 degrees Celsius. The UK aims to reduce greenhouse gas emissions by at least 68% by 2030 compared to 1990 levels as a frame of reference. This requires innovative solutions. So as you can see, the temperature map on the left there shows the UK over time period with recorded temperatures. As time has gone on, the temperature has gotten hotter. The map has presented this as a darker color. So in order to avoid something like this from progressing even further, we need to start tackling the emissions that we start having. Looking at the graph on the right-hand side, you can see that the metric tons of carbon dioxide per year has been reducing on a steady trend, originating in 1990 at 800 million tons, and slowly moving down towards just shy of 400 million tons by 2024. So this emphasizes the desire for greenhouse gas emissions in total by using a unit of measurement of the million carbon tons dioxide to equivalently track down and see the ultimate goal of limiting global temperatures by 1.5 Celsius in line with the Glasgow Climate Pact. Next slide, please. NETs are also known as carbon dioxide removers or greenhouse gas removal technologies. They are innovative approaches aimed at extracting carbon dioxide from the atmosphere and sequestering it over extended periods. These technologies are anticipated to play a crucial role in climate change mitigation and achieve net zero targets. So, carbon capture is a critical stage in evaluating during the life cycle of a BECS assessment. The effective carbon capture ensures that the CO2 produced during biomass energy conversion is minimalized, contributing to a negative emission. So obviously biomass has grown over a period of time. The process of photosynthesis requires carbon dioxide in order to produce oxygen. And then in addition to this, once the biomass is burned in the process, that carbon dioxide is recaptured and stored, reducing the amount of carbon dioxide released to the atmosphere and effectively making it a negative or zero emission process. Next slide, please. So I compared three biomass feedstocks, switchgrass, wheat straw, and corn stalks across two different energy conversion pathways. These pathways were combustion with post-combustion carbon capture and gasification with pre-combustion carbon capture. Process, as you can see on the slides there, have the various stages of gasification, combustion, pyrolysis, liquefaction, and furthermore have multiple stages in order to release the energy from the biomass and then store the emissions that are released from that. Next slide, please. These methods are key in energy conversion methodologies, being one of the most widely used pathways for biomass energy conversion due to its ability to process diverse feedstocks and produce various energy forms. As you can see on the slides above you, the gasification and combustion approach are two similar processes, but require slight adjustments in their process mechanism. So gasification requires more preheat compared to combustion. The reason for this is in order to release the syngas that is trapped within the biomass and create biochar, whereas combustion has no concern for this and is able to just ignite and go from there. Preheating will help with the efficiency, but it's not a requirement as it is for gasification. Next slide, please. So the methodology for my assessment was first to, as with anything, you have to research the topic to find out more about it, which incorporated literature reviews of technologies, determining what process steps we require, how the process is laid out, what feedstocks are viable, and this was done in conjunction of what feedstocks are available and plentiful in the UK to do it as a realistic assessment. Next was followed by data collection, and as I progressed this into the modeling step, I would have to circle back to the data collection again as I found more inputs that were required for the modeling software known as CCalc. After completing the process modeling, then the economic assessment was to follow. Obviously, we are dealing with massive pieces of equipment and incredible costs, so determining the feasibility of the process, determining the viability and cost of the feedstocks, the outputs, and whether the efficiency is maintained on scaling up is essential. As with most process systems, the bigger you make it, you can't use the same numbers scaling up. You have to adjust in order to try and get the same conversion factor. And sometimes, unfortunately, you can't retain the same efficiency that you had on lower scales. All of this would be put in to be evaluated to see if it is a viable cost. This is then followed up by the evaluation and results based on factors for performance, climate impact, and possible drawbacks. Next slide, please. So the data inputs for the BECS model using CCalc include multiple inputs that aren't just based on the actual process. Factors like transportation are considered as the distance from your farm to your process plant weighs into it. The method in how you transport it weighs into it. This is not the only one. So due to the nature of BECS, you're considering the entire life cycle of anything that you are using. So when you transport, you account for the diesel used in that, how that was produced. When you use chemicals, you account for the process in order to generate those. When you're using water, that counts as an assessment for it, even though you have to irrigate your crops. It's all included and it's all part of the assessment. So the more of anything you use, the greater your aspect climbs and climbs in terms of what your BEC's impact is. Next slide, please. So what were our findings? One of our findings was that we had a much better carbon footprint from wheat straw when we use the combustion method. So as you can see there, we got about negative 833 kilograms of carbon dioxide per megawatt hour of energy generated, meaning that every megawatt of energy that we produced, we generated every megawatt hour of energy that we generated, we offset by negative 833 kilograms of carbon dioxide due to the carbon capture process, as well as the factor of wheat straw being able to absorb and photosynthesize, reprocess carbon dioxide into oxygen. Next slide, please. But just because it performed best doesn't mean it was the most economical. So in this case, gasification of wheat straw emerged as the most cost-effective option. Now, this begs the question, which do you pick? Do you pick the cheapest and most economical, or do you pick the most environmentally friendly process? Next slide, please. Now, the feedstock you used might change in the future. So if you were to go on the case of gasification emerging as the most economical process, but in the future, your feedstock might have increased in price and you have to look at an alternative. Now, you've stuck with your process. As I explained before, the method in how they are done are quite similar, but there are differences. But considering you're looking at the production scale, you're looking at massive pieces of equipment that you've bought, that you've maintained, that you have connections between the two, where you might not have a connection that bypasses the system. So now, if your feedstock changes over time, can you account for the flexibility of using another feedstock for the same process? However, each feedstock has its own makeup. And because of that, the emissions that it releases aren't all the same. So taking, for example, corn stalks, it has a higher human toxicity potential compared to the other feedstocks. Now, you can look at the significant difference in that graph if you had selected gasification as your process, but at some point wheat straw became far too expensive. There became an issue with it. There was a shortage of supply because it is something that is easily burnt if it was a dry year. You could lose everything and have to swap to a feedstock that now has a much greater human toxicity. You can see switchgrass also has a higher toxicity value, not as significant, but in comparison to wheat straw, far more significant. Next slide, please. So another thing to consider, as I stated before, is hotspots of the process. Now, through modeling, I was able to find that hotspots that were responsible for a greater proportional amount of emissions when compared to the rest of the system. Now, this was generally located in the cultivation phase, which seems to follow logic, as this would be the longest time period for the growth, compared to obviously burning it being much quicker. This would require the most inputs. You're talking about water, you're talking about human intervention, you're talking about irrigation, chemical use for fertilizer, chemical use for pesticides, for herbicides, for insecticides. All of these factors play a part in what your assessment is going to do. And generally, this resulted in the cultivation phase being the highest phase. Your source of water also plays a part of it. If you use river water that's abundant and nearby you, it's a much smaller impact. If you have to pump it from the water supply, that starts scaling up. If you had to bring water in because it was a dry year, your implications will go much greater because bringing the water in If it's on trucks, results in diesel use, which then raises your emissions for that. So all of these can play a factor into it. So the other aspect is all of these emissions, when used at the farm, are not captured in the process. Yes, the plants are absorbing in order to convert for photosynthesis, but whether you spend more or less diesel in your farm equipment to achieve this isn't considered. Whereas at the production plant, the more carbon dioxide you generate, you'll have an efficiency that is captured down regardless. Next slide, please. But similarly, with hotspots appearing in the processing and modeling scenario, that's not the only place that they could form. In other scenarios, you can be looking at the carbon capture chemical that you use. So in this case, MEA is the solvent that is used in order to trap and remove carbon dioxide from the emission gases that you use. It does this by passing the gases through the stream with the solvent, and that strips out the carbon dioxide at an efficiency value, leaving things like carbon monoxide, SOx, and NOx untouched. But these aspects can poison the chemical that you use in order to remove the carbon dioxide. But because this is a chemical, it means that it was produced, it was transported, it was mixed with things, it has its own waste that's associated with that. And that means that the more of it you use, the greater your impact is of when you're assessing your own individual carbon emissions. Another aspect is economically, the situation for cheap feedstocks or chemicals could change. It could become banned, which occurred when I was researching on different chemicals that I could use for the process. I found that some were no longer able to be used in the UK, some were no longer able to be used in Europe, which then could mean your next viable alternative is much more expensive. Your entire cost for your system can suddenly become uneconomical and change what you have. A similar example for this is, say, diesel cars. So in the UK, diesel cars were greatly pushed about 20 years ago. But as time has gone on, diesel cars are no longer seen as the promising alternative to petrol cars. So all the government grants that were originally given out for them have now been scrapped, discontinued, and all of the diesel cars are now trying to get removed from the road because of the additional emissions that they have. This is something similar that you could see in your production plants. You could completely establish your plant, and then a newer, more effective, more efficient technology could be discovered, and that could drive away investors and drive away government grants, regulation that you previously would fall under. Next slide, please. Now, looking at this video, we can see the influence of public policy importance. So the first step in public policy is problem identification. As you can see in the video, the emissions have increased over time and have points of accelerated growth and then stagnation and sometimes decline. As society became more aware of the issue of greenhouse gases and emissions impact on the world, you can see efforts were made to reduce the amount of emissions generated. However, this is not the case for all emission sources, and highlighting how policy changes locally are beneficial, but global sources need to be held to the same standard to achieve a more sustainable outcome. My research helps quantify the problem of greenhouse gas emissions and highlights the potential of BECCS as a solution, and also demonstrates how specific feedstocks such as wheat straw could improve a BECCS cycle. Next slide, please. Okay, now we move to policy formation. Based on my findings, what policy options can we consider? Now, should we consider subsidies or tax incentives for utilizing wheat straw in BECCS, given its superior carbon footprint in combustion? Should we apply regulations or stricter emission controls on gasification plants using corn stalk to mitigate human toxicity potentials? Should we offer incentives for carbon capture technology development, particularly for wheat straw combustion and gasification, mentioning how, well, not to mention how we can see the carbon price mechanisms for that. Policies to support sustainable agriculture practices and minimize emissions for biomass cultivation could be implemented. Of those, which policies would be best? Now, given wheat straw's negative carbon footprint in combustion, policies should probably incentivize this using subsidies, using tax breaks, or mandates to incorporate it in bioenergy production. Now, when it comes to mitigating the high HCP human toxicity of cornstalk gasification, policies probably should implement strict emission controls or discourage this pathway altogether. Now, this is something that assessments should probably focus on. Unfortunately, cornstalks is quite a common crop, and that'll come in later when we start considering the actual implications of whether you prioritize using a crop-based feedstock or using just a plant when we get into the ethical concerns. Now, incentives for carbon capture technology develop, particularly for wheat straw and gasification, could end up being what solves this problem. But you have to keep in mind that there could be shifts in the price for this. There could be a bad financial year that makes this unviable. There could be destruction, arson that ends up destroying croplands that you wouldn't be able to use your sources for. Next slide, please. So policy adoption isn't always straightforward. There's several barriers that can hinder it. So social acceptance is a big thing. Public perception of BECCS and carbon storage can influence policy adoption. So how can we build public trust with the support? In Australia, they had a statement for biomass plants and anaerobic plants, which had an approach of not in my backyard. People were for the concept in theory, but didn't want it around their area. That plays into factors of wondering what your local community's resale and value will be once you have an industrial side to it. People are worried about property values, are worried about what emissions and odors they will come up to, are worried about the increased traffic if there's more trucks going down their home lanes, and general safety for it. So that's something that you will have to address every time you try and do it. It's not just a matter of trying to make the world a better place. People are generally happy with the concept, but aren't as happy with the concept being applied into their area. So the availability of CO storage is also something that adds further complexity. You can capture carbon dioxide, but where are you going to put it? Generally, these are stored deep underground in secure natural formations, but that requires drilling down. People tend to worry about that. In some areas, drilling can disturb your bedrock, and people worry about earthquakes or any other implications that you could have from your land shifts. So another thing is the economic viability. BECCS can be more expensive than traditional energy sources. So how do you address this cost gap? Are you going to subsidize the technology indefinitely? That requires raising taxes, raising commissions for the government's services in order to allow the additional power generation at a higher cost while trying to keep it competitive. Obviously, R&D generally has a higher tolerance and a higher cost at the start until the technology proves itself and is able to generate a greater return. But what we do tend to see for renewable sources is they aren't as energy dense as fossil fuels, which means you could be paying more for less. And how long in hard economic times is that viable for? Another concern, and this goes to an ethical one, is land use concerns. So at large scale, you could have biomass production that could end up competing with food production and ecosystem services. So what safeguards are needed to make this socially acceptable in public perception? So you could end up, instead of having, if you are subsidizing this, instead of someone producing edible crop, they could swap to a more energy dense but not edible feedstock for back storage. So the overall cost of food could increase at that time. And with reduced demand, obviously that has the impact on a reduced supply that has the impact on the cost of demand. So how can we build public trust and support for this that it won't happen? Next slide, please. So next one is policy implementation. Effective policy implementation requires careful design and the right policy instruments. So renewable energy standards, including BECS in renewable energy mandates, can drive demand. Research and development grants supporting innovation in BECS technologies can lower the cost and improve performance. Carbon pricing can create a market of carbon removal incentives and BECS deployment. So this is based on the fact that in the UK, production plants are allocated a certain carbon emissions allowance. Carbon credits is what we call it. Carbon credits are not fixed to your plant. If you do exceed them, you'll pay a penalty for it. But if you are able to implement carbon capture and reduce your actual emissions, you still have your carbon pricing allocation. So what companies will do then is they will lease out their rights to other companies that are either exceeding their time, have older technology, aren't able to make the change. And that not only then makes you more environmental, it also allows you an additional source of income from a reliable business while you are doing the right thing. This requires clear regulatory frameworks and policies to address the obstacles. And carbon capture generally does get positive public engagement, and policies should address any concern that result from this. Generally, carbon capture is on existing production facilities. So adding another unit of production on an existing plant should probably not cause any issue, but it is always good to highlight the positive impacts you're trying to make for the local community. Next slide, please. So the final stage is policy evaluation. How do we know if BECS policies are working? Can we track the amount of CO2 removed by BECS projects over time? Can we assess the cost effectiveness of BECS compared to other carbon mitigation strategies? Are we able to monitor the environmental impacts of BECS, including air and water quality, biodiversity, and land use changes? And really, what metrics can we use to evaluate the succession of BECS policies, and how can the research contribute to ongoing monitoring and improvements? Now, this should be fairly simple to implement in many ways, because in order to capture the amount of carbon dioxide that you put in, you need to evaluate the efficiency of your chemical, the efficiency of your process, and you can only saturate and store a certain amount, which means that you have a figure of how much you've produced. That over time is easy enough to keep a digital track record of now and log in order to show how much you have removed, including air and water quality is something that you can probably test, but would be up to public perception and is not really something numbers would necessarily convince people about. Okay, next slide, please. So let's take a closer look at wheat straw. So far, we've spoken about how it was the best economical and the best environmental. Let's have a deeper look into that. So my research clearly demonstrated its potential for significant negative emissions, especially when combusted. And this is due to two main factors: the high levels of the fuel source and the carbon allocation due to wheat being an edible product. So if you use an edible product as opposed to just a feedstock that cannot be consumed, you are not then using a co-product or a byproduct. You are growing it purely for one process, which means all of its allocation for emissions can be attributed to your process. But if you are growing something like corn stalks or wheat straw, you have a co-product, the wheat and the straw, or the corn and the stalks. Now, when you come to account your cultivation, which I said was generally the greatest hotspot for emissions, when you come to contribute that, you can actually allocate it in a split between both of the emissions, which artificially makes it look like it's lower, but you're getting two products feedstock, essentially. So what you should do is incentivize the use of biomass feedstocks that can generate a co-product. Obviously, straw can be used as animal feed, can be used in thatch roofing, can be used in brooms, other less advanced technologies, and can be used in biomass production. And the other section is, since it's quite thin and it's a very relatively small stalk, it's quite easy to dry out, it's quite easy to cut up, it's quite easy to bale. You don't need massive equipment as something that's quite a bit thicker. Like corn stalks would be about an inch in diameter, whereas a wheat straw would be probably a couple of mils in diameter. So what we should do is support research into optimizing carbon capture technologies tailored for feedstocks that can be used as co-products, such as wheat straw, and consider the regional variation of what is available and grows best in that area when designing policies. One solution will not probably fit all. Next slide, please. So based on these findings, I propose the following policies recommendations for the UK government. I would establish a wheat straw BECS incentive program and offer subsidies or tax breaks for power plants using wheat straw with carbon capture. I would invest in research and development to advance carbon capture technologies specifically designed for wheat straw combustion. I would implement a strict regulation on emissions for gasification plants using substances like corn stalks that have a higher human toxicity value and provide incentives for cleaner technologies. I would promote sustainable agricultural practice through farming education and financial assistance. Obviously, the more you use carelessly in the cultivation stage, the greater your emissions will be as a concern. And I'd also support development of CO2 transport and storage infrastructure to address this. Now, I only assessed 3 feedstocks, so this will be based on my assessment between wheat straw, corn stalks, and switchgrass, but there may be a more appropriate option that I haven't assessed. Next slide, please. So, while BECS offers potential climate benefits, we must acknowledge the ethical concerns I mentioned earlier. So large-scale biomass farming can lead to deforestation, can displace rural communities, and impact ecosystems. Furthermore, it can divert land from food production, potentially exacerbating food security issues, and it is important to explore if we should use land for food or energy. For something like wheat straw, we are able to use it for both. But what happens if we scale up the production to a massive amount and we have too much wheat that we aren't selling or do anything with? We're just essentially producing it in order to say on paper that we have done this economically and environmentally, but in reality is leading to a great amount of waste, which the wheat will be seen as a product when it comes to an BECS evaluation. It will not be considered a waste even if it goes to waste, which is a hurdle in the principle of it. So wheat straw did turn out to be the most viable out of those I evaluated, but a better alternative could be there. Alternatively, if wheat straw was the best option, then the world, like I said, would increase the wheat farming, and the result was ethical concerns of whether you would end up just wasting the amount that you generate. Next slide, please. So, what if instead of growing our fuel sources, we use what we have already? So, this is a concept that I didn't consider and was outside the scope of my MSc, but is something that can be further researched to consider its viability. So, what about investigating viable alternative technologies? One of them being anaerobic digestion. So the process of anaerobic digestion is to convert food waste and sewage into biogas through the natural process of organic breakdown. But this occurs in an artificial environment to accelerate the breakdown. Now, this is done by controlling the temperature and moisture levels in an airtight environment with the feedstock and a preloaded microorganism to kickstart and reduce the growth period of organisms that will carry out the breakdown. So the outcome of this, as you can see, is methane gas, which is a renewable energy source in this consideration, and a digestate fertilizer. So this would reduce the time period that would take for normal biodecay from over a year naturally to a matter of weeks in an artificial environment. So you can see there that they have massive tents, they almost look like tents, that are trapping the gas and allowing you to siphon it out. So the importance is to keep the system airtight with an absence of oxygen, which are going to slow down the rate in how the organisms multiply and accelerate the breakdown. Next slide, please. So aside from you having a clean energy source, you also have to consider, as I said, the digestate fertilizer. So instead of landfills now having waste, and which attracts pests, you are able to capture all of it inside this anaerobic digestion plant and use it in order to create a fertilizer that's already broken down, so no concern for pest control, and you're able to generate a clean energy source. So, as I said, this reduces landfill waste, which play a part in community pest control. With this improved, that means there are less pests that are able to spread diseases. Now, similarly, like I said, you can use food waste. You can also use sewage as a feedstock and wastewater. So there are already established infrastructures for collecting sewage, which can be leveraged for the biogas production. So further reducing odor impacts in local community because all of the gases are trapped in oxygen's airtight environment for the methane production. So although these methods don't reduce carbon dioxide production, they do help create a more clean power source and reduce additional carbon dioxide production by not having to use a fossil fuel version of fossil fuel version of methane. Next slide, please. Another consideration is bioalgae. So we've looked at artificial carbon capture. Now, obviously, all plants participate in carbon capture when they undergo photosynthesis. Maybe there's a way to combine the natural process as well as combining the existing infrastructure process. So if the goal is to actively remove carbon dioxide efficiently and effectively, then we can explore bioalgae tanks. Algae requires a small area and they have a high CO2 absorption rate that can be 10 to 50 times that of biomass farmlands of equal area. Now, this is because the farmland crop's absorption is limited to the leaves, spacing of each individual plant, and the organic function. Obviously, a crop is trying to grow food, so its energy is going not solely to the conversion of carbon dioxide to oxygen, it's going to be split between growing the plant, growing the food, as well as converting the oxygen. Now, although algae farms would require significant capital costs and the regulation to maintain them, in warm climates such as Mexico, the energy input is further reduced and the system requires less labor than traditional farms, since it's all going to be in tanks. Any change that you make can spread across the entire tank as the water is pumped around. So you don't have to worry about pests. You don't have to worry about weeds. You do have to worry about other algae organisms that could overtake the production if they contaminated. But considering you could dose into one system as opposed to try spread it evenly across using farm equipment, I'd say that does make it easier. Now, there's also the added benefits of algae having co-products. So algae can be used to create biofuels. It can also be used as a food supplement, and it can also be used as fertilizer, which helps impact what your BEX assessment would be for this, which obviously I haven't done, but it would help generate an additional waste once you swap it out for a new, fresher, younger crop circle. So the biggest benefit being the ease of installation in different settings when compared to a farm. Obviously, a farm can only be done in big open areas and generally is reserved for rural settings. But considering this can be done in a tank pretty much anywhere, there's a benefit to it being able to be installed in a city center, which has an abundance of greenhouse gases from emissions and additional population concentration, giving you the ability to possibly convert emissions and carbon dioxide in the most polluted areas to try clean up the area there. There's little reason to try and improve the air quality in very rural areas that have farms, forests, big open out spread land, which likely will have the best the best air quality that we already have. Maybe we should focus on trying to improve the air quality in cities rather than in rural communities. Next slide, please. So cities often experience something called an urban heat island effect. So this is where the temperature is significantly higher than surrounding rural areas due to the increased greenhouse gas acting as their namesake and trapping the light and heat in an effective dome around the city. The other aspects in the additional heat, the other aspects is the additional heat from cars, from residential and commercial heating, and the lack of green spaces absorbing and converting the heat generated from sunlight is instead replaced with materials of construction such as concrete, cement, tar, which absorbs and retains the heat and then releases it slowly over a longer period of time. This explains why cities are generally much warmer outside at nighttime compared to a more rural setting. So a warmer environment will assist bioalgae tank growth and reduce operating costs for heating. Effectively, this can help reduce the heat in the city by absorbing the heat from the environment, which will provide a cooling effect for the city. Additionally, the emissions absorbed by the algae improve the air quality for a condensed population and can help improve residential health. So, the compact nature of algae means that for essentially the compact nature of algae means that a forest can essentially coexist within a city, providing the benefits while minimizing the expected accompanying requirements, such as land space or constant water requirements for watering. You will still need water for the algae tanks, but you aren't required to effectively continue watering the same degree as massive trees and forests would take, or as crops would have, where there's runoff, there's evaporation, there's other aspects that will reduce the effectiveness of your watering. Another thing you won't have to consider is the soil quality and depth. Obviously, in forests, bigger trees that you need to have better soil quality reaching further down for the roots in order to grow healthily. In an algae tank, as long as you put nutrients into the tank, which generally could even be something like sewage, making it dual purpose, you will be able to increase the growth and you can monitor the levels quite easily with pH, with other digital aspects, compared to a wider surface area of farms where you'd have to individually survey each crop across a greater area. Next slide, please. So, what policy recommendations can be done if we consider a diverse approach? So, we should embrace diverse approaches purely because one solution will not be appropriate, not even for matter of within different countries, but within the same country. So, This could include supporting BECCS where sustainable biomass sources are already available. So in terms of rural areas, we can probably build BECCS plants there to minimize the travel distance between them and essentially make it a farm to table setup. This also will improve the amount of available jobs in the area. When we get to more urban areas, maybe we should start incentivizing anaerobic digestion for waste management. So this is going to be promoting um, local communities that are higher density when we talk about suburbs or cities in apartments to separate what they have as food waste in order to reduce the pest growth that they have in the local community, which is a general issue that they tend to have. Separate that, send it specifically to a anaerobic digestion plant that is able to maintain and trap the gas, which is minimizing the impact of the emissions, and is also cleaning up the air quality in the surrounding area, doesn't impact the residential community surrounding it from odor that is released, which will generally help promote people's outdoor health as well as property value. Another aspect we can promote in cities and urban areas is bioalgae installations. These can be done either at ground level, parking garages, could be on top of every building have a small enough tank that the structures can support it. But because of how effective it is and how the surface area essentially can equate to a forest, you could essentially put one on top of every building and have the equivalent of a much bigger green space. So, of course, all the technologies face a challenge, but future research can help address this. Next slide, please. So, action can be taken by farmers when it's considering the BECCS assessment. This can also be done by governments and companies in the energy sector. So, in order to address challenges and future research, BECCS deployment needs to be further researched in order to see how the long-term impacts and large-scale biomass production on land use and biodiversity can impact the system. Next slide, please. In terms of anaerobic digestion, of course, these technologies face challenges in order to get the local community to adapt from putting all their waste in one bin to separating out food waste, ensuring that that is equally nice and contained when collected. It is stored somewhere when it is changed from the normal landfill to a specific landfill to reduce the amount of pests before it is introduced into the anaerobic digestion plant. As I said earlier, the time period can be a matter of weeks. So as you build one, as you process one amount of feedstock, you will be collecting your next feedstock. You have to ensure that that doesn't end up having pests as well. This is something that would require public policy, public involvement, as well as include future research and government policy. Next slide, please. For the term of the algae, as you can see there, the amount of CO2 efficiency compared to land footprint, there is not even a comparison between how different traditional forestry and BECCS crops are when considering the bioalgae efficiency and the land footprint. So the techno-economical analysis of BECCS is different in regions across the UK, and considering local biomass and availability and infrastructure would probably alter the perception of this graph, but this is just taking it as an average. So in rural environments, the best method would still be BECCS. However, in urban settings, bioalgae is a better method, in my opinion. And anaerobic digestion is an application to both environments for reducing pests, but a larger scale feed source, such as a city, would mean a higher turnout rate compared to the population size that you would have in a rural environment. Might not be enough for a large scale anaerobic digestion plant. And a matter of fact, in some rural communities, there isn't set up sewage infrastructure. They might be able to do one locally for their own residential area, but they might not be able to have enough or have the infrastructure in order to make this a viable option. So development of more efficient and cost-effective carbon capture technologies could end up appearing that could solve some of these issues and make it a more viable alternative. Next slide, please. So, in conclusion, my research provides valuable insight for policymakers seeking to leverage BECCS for climate change mitigation. By carefully considering feedstock selection, conversion pathways, and policy instruments, you are also prompting an alternative technology that can move forward to a closer, sustainable future. So thank you very much for listening. If there's any questions, I'll take them.